Greetings, my name is Luis Javier Ontañón, and on behalf of my coworkers, I present this work entitled Control Bifurcation in the Rössler System, Design and Analog Implementation, in which we develop an electronic dynamical system whose parameters can be automatically controlled in order to study bifurcations with its states. The presentation will be divided in three parts, namely, the bifurcation in dynamical system, a brief explanation, how to scale the Rössler system in order to adjust it to electronically implemented values, and how does the control analog bifurcation works. Finally, the conclusions. And commencing with the first topic, a brief explanation of bifurcation in dynamical systems. The bifurcation on a dynamical system can be understood as the variation of the parameters in which the dynamical system may result in a change that can be appreciated in the topological features of the flow of the system. The resulting trajectories in the phase space can take either periodic behavior, non-periodic behavior or chaos, or even stabilizing fixed points. A good example of a bifurcation can be observed in the well-known discrete logistic map. Here, it can be appreciated on the graph of the left-hand side, the bifurcation diagram of the system, and on the right-hand side, the x-state for each given value of the parameter b. Notice that the system presents repeated values in the x-state for some ranges of the parameter, depicting chaotic behavior, periodic behavior, or even fixed and stabilized points. Here we can appreciate how the system presents two values on its state variable, presented period 2. Continue the bifurcation to period 4, period 8, chaos, period 6, chaos again, period 5, a brief region of period 3, and chaotic region again. We base this work on the chaotic benchmark Rössler dynamical system. The Rössler system is described by the following set of three-state equation, in which the variable key corresponds to the states vectors of the system u, v, and w, and the parameters a, v, and c corresponds all to real values. In this case, the system is chaotic for values of a and v equal to 0.2 and c equal to 5.7. Here, it is shown two projections of the solution of the phase space of the system, which will be considered as bar phi. Notice the values that the states take. For instance, in the projection of the left-hand side, the range is between -10 to 15 for the variable u, and from -15 to 10 for the variable v. On the right-hand side, the values for the state w range between 0 and 25. Considering analog components such as operational amplifiers, these values exceed the voltage limit that the components can process without reaching saturation. Therefore, escalation on the system is needed before the electronic implementation. So now, an explanation on how to adjust the states of the Rössler system. We will consider the following transformation. For example, the variable x will be u divided by a factor named epsilon. The same thing for the variable nu y and the variable c. In this case, these are the resulting states of the system scale. Now, a value of epsilon equals 10 will be considered. Here, we can see both of the projections of the system. In this case, notice now how the value x is ranging between -1 to 1.5, the variable y is ranging between -1.5 and 1, and the variable c is ranging between 0 and 2.5, instead of 25 as it previously did. Now we can continue with the electronic implementation of the system. But first, let's explain how the bifurcation in the phase space of the system will be considered. We will use a Poincare plane which is defined by the following equation. in which the values of alpha 1 to alpha 4 are the coefficients of the hyperplane. We need that the location of this Poincaré plane is transverse to the flow bar phi. The idea is to capture the crossing events of the flow bar phi in a specific time tau. This set of crossing events will be plotted versus the specific value of the parameter, and the graph of this will be the bifurcation diagram as it is depicted in the following slide. Here, on the graph of the left-hand side, we have the bifurcation diagram of the system for the values of p ranging between 0.01 up to the value of 2. And in the right-hand side of the projection of the flow of the system for each given value of the parameter p. In both of the graphs, the red line corresponds to the position of the Poincaré plane, and the crossing events of the flow of the system with the Poincaré plane are depicted with black crosses. Notice that the system presents periodic behavior and chaotic behavior for specific values of the parameter b. This was implemented by means of numerical analysis in the MATLAB software. For example, here the system presents period 2 converged to period 1. For lower values of p, we have period 6, a region of chaos, a brief region of period 3, chaos, converging to period 4, and again period 2 and later period 1. Now, the construction of the electronic implementation will be discussed along with the control analog bifurcation. The following circuit diagrams depict the analog construction by means of operational amplifiers of the system. Here, in the upper part, we have the circuit for the variable x, and in the lower part, we have the circuit for the variable y. A more detailed explanation on how to construct these circuits can be found on the reference number 5. Here is the schematic for the variable c. Pay special attention to the components U5 and U6. These are two digital 100 kilo ohm potentiometers, and they are both controlled by the Arduino Uno embedded system. These potentiometers will control the gain for what it will become the specific parameter b. After this control change in the bifurcation of the circuit, the voltage solution of the states of the system will be captured by a National Instruments MyDAC acquisition board and will be processed in the computer again with the MATLAB software. The flowchart of the experiment is depicted here. First, an initial value of p will be adjusted to 0.01. This value will be increased, so the parameter ranges between 0.01 up to the value of 2. Then, the variable k stands for the data acquisition of the circuit. We'll only capture 10,000 samples of the x and y states for each specific value of the parameter b. With the acquired data, MATLAB will check for the crossing events of the Poincaré plane, which in this case will be located in y equals 0. These events are then plotted in the bifurcation diagram as it will be depicted below. This is the experimental result of the control analog bifurcation diagram. Notice how does the electronic system, due to the precise assignation of p, results in an almost identical bifurcation diagram as with the numerical simulations. Here, as mentioned before, the variable b is ranging between 0.01 up to the value of 2. We can easily see that there are some values that correspond to the numerical simulation. For example, the values of chaos, period 3, period 4, a wide range of period 2, and period 1. Now, the voltage measurements in the oscilloscope of the circuit for some fixed values of the parameter v. In this case, we have a chaotic region with the value of b equal to 0.2. Here the system presents period 3 for a value of b equal to 0.38. period 2 for a value of b equals to 0.1, and period 1 for a fixed value of b equals to 1.5. Finally, to conclude this work, we have the following notations. First, the control bifurcation presented here didn't use sawtooth or continuous voltage ramps as it was used in other works. Second, that the bifurcation parameter value which is needed to change can be controlled precisely with the embedded system. Also, there is no need to disconnect the electronic components in order to change the value of the parameter b. And finally, different control bifurcations can be further studied with different parameters, different range of values, or even different bifurcating systems. To conclude, the authors want to thank the support of this work by the following sponsors.